or particle. Before we travel on, we need to really understand the medium we are moving in. If we don't do this, the pilot assures us we will understand little bit what we see, and in particular the interior of Atomland. The target of our next voyage will be in the impenetrable jungle. The coastline already appears closer, though we have barely left port. What the pilot has to tell us is so weird that he knows we may not believe him, so he urges the captain to drop anchor and assemble the crew below the decks for demonstration. After a few moments preparations in the pitch black hold of our ship, the pilot fires a beam of laser light at the screen with two small slits in it. On the other side of the screen is a detector to monitor the light that make it through the slits. The first things to note is that the light behaves like a wave. If the slits are narrow enough, the slits themselves start acting as a source of waves. That is, the light deflects as it passes through the slit, just like the water wave in the narrow channel in the harbor. This indicates that the light has a wavelength, which is similar in the size to the width of each slit, just as the water waves that deflect the most had a wavelength similar to the width of the harbor entrance. Furthermore, we will see the pattern of the bright and dark bands with our detector. At each position on our detector, light is being received from two sources. The two slits, like the two splashing dolphins near the harbor. 4 points exactly halfway between these slits, the light travels the same distance from each slit, and the peaks of the waves from each slit will arrive together in the phase. The peaks reinforce each other as do the trough, leading to a strong wave and thus a bright light. For any other point, the light travels a different distance from one slit than the other. The adding up is not guaranteed. If the differences in the distance traveled is a whole number of the wavelengths, the peak from the one source will arrive with a different peak from the other, and things will still add up. But if the difference is a whole number plus a half, the peak of the one will arrive with a trough of another. The waves are in antiphase. The waves are in antiphase. These are the dark bands where the peaks and troughs cancel each other. The detector will remain dark, just as the seagull rested at peace in the bay. This seems pretty conclusive. Diffraction and interference are going on, and they only happen with waves. We would not see this behavior with particles. We can even work out the wavelengths of the waves, not something that makes any sense for a classical particle. Light is a wave. End of story. But it is not the end. There is a twist, an important twist. The pilot urges us to look a bit more carefully at the detector that is measuring the light once it has passed through the slit, creating the bright and dark interference bands. The detector in our experiment relies on the photoelectric effect. That is, when the light hits the detector, it releases the electrons, which can then carry an electric current. The explanation for this behavior lies on the coast of the Atomland. But for now, we see that by applying a voltage to the detector, we can make the current flow and detect the freed electrons. This is how we know when light hits the detector, and thus where the bright bands are and where it is dark. Wave moves energy around. That's what makes the seagull move, and that's what releases the electrons. in our detector. That's what releases the electron in our detector. And with waves, there are two ways the amount of energy can be increased. You can increase the amplitude of the wave, which makes a girl bounce higher, or you can increase the frequency of the wave, which will make it bounce up and down more often. The same is true with light. The power of the laser can be increased either by making it brighter, more intense, or by increasing their frequency. The frequency for light corresponds to the color, so increasing the frequency might mean moving from the red light to the blue light, say. In our experiment, however, these two different ways of increasing the power have very different impacts on our light detector. One would expect that when the amount of the light shining on the photoelectric material, such as our detector, is increased, the electric current would also increase, and this is true under some circumstances. But it doesn't always work like that. Say, for example, that light we are using is blue. This means it has a wavelength of 475 billionths of a meter, corresponding to the frequency of 650 terahertz, 650 trillion oscillations per second. The light detector registers the light, producing our lovely interference pattern of the bright and dark bands, and clearly demonstrating the wave nature of the light. If we increase the power of a blue laser, the intensity of the light registering in the detector also increase. Sure. All well and good. However, we now tune the frequency of our laser. We reduce it, making the light first green, then red. For this particular detector, as the frequency reduces into the red, the electric current suddenly dies away, and we can no longer detect light. As we reduce the frequency, we are reducing the power of laser. If this were the wave in the bay we were dealing with, we would be making the girl bounce less often. So it is not surprising that we get less current, though it is a bit surprising that it drops so suddenly. No matter, we can compensate by the turning up the intensity of the light, corresponding to the making the girl bounce higher, even if it is bouncing less often. What we would see is disappointing. In fact, we would see nothing. Once the frequency has dropped below the certain value, which depends on the detector we have and exactly what it is made of, we have no electric current no matter how high we turn up the intensity. This is impossible to explain using the continuous wave of light. The energy is there. Why does it not free up any electrons? This can only be explained if the light comes not as a continuous wave, but in the little packets or quanta of the energy, more like the letters the crew sent home than the radio waves we use in the emergencies. Sure. For light, the packages are called photons. A single photon is a quantum of light. This is the explanation Einstein put in the breakthrough paper of 1905. The energy of the individual photon depends on its associated frequency. Blue photons have more energy than red ones. The total amount of energy in the laser beam is the number of photons multiplied by the energy of each photons. When we turn up the power of the red laser, we are increasing the rate at which photons are emitted, but the energy of each photon remains the same because the frequency of the light does not change. Sure. Conversely, as we turn down the power of the blue laser, we reduce the number of photons, but not the energy of each photons, and so As Einstein said in his paper, there is indeed no lower limit for the intensity of the exciting light below which the light would be unable to act as an exciter. Acting as an exciter in our case means releasing an electron and thus registering in our detector. This is presumably more elegantly put in the original German. But the result agree with the experiment and is exciting in any sense. What is meant is that even a laser turned light down until it emits only one photon a year would still eventually build up the interference pattern of the light and the dark bands. One spot at a time, light comes in the discrete packets as thought it considered of the particles, but exhibits interference as though it were a wave. Light comes in the discrete packages as though it consisted of the particle, but exhibit interference as though it were a wave. Put together the fact that on the one hand, light exhibit wave-like properties such as interference, but on the other hand, also comes in the discrete packets with an energy that depends on the frequency, tell us that it is neither a wave nor a particle. Tell us that it's neither a wave nor a particle as we know them classically. It is something else entirely. At low intensity and high frequencies, we have entered a new regime of the physics, and we need a few set of concepts to describe it. Photons are excitations in a quantum field. The quantum field is a sea that we are sailing on. The pilot is looking quite smug at this stage, and he made a captive audience of the crew. His demonstration has got our attention and got us closer to understanding what quantum field is and how it works. But we needed to know more, and he's only too happy to tell us.